All right, this is my solutions video for my worksheet on rotational equilibrium and dynamics. We have a ball of class of we have a ball of clay with mass m falls straight down and sticks horizontally to a horizontally spinning disc. So let's envision this disc, and it is spinning, and so it has some angular angular speed, and the disk has a mass of 10 m, and it is a constant angular speed, so its acceleration is 0. And I have this piece of clay that's going to fall and stick on this disk. Describe what happens to the system's angular momentum, angular speed, and the moment of inertia. And the system has been defined as the ball of clay and the disk. And so angular momentum, what is it going to happen to it? Well, the angular momentum initial is the rotational mass or rotational inertia of the disk times its angular speed. The ball is not moving, and so it has no angular momentum. And the angular momentum final is going to be the same. It will be I final times omega final, but these are going to be the same because the outside torque is equal to, there's no outside torque, therefore momentum is, okay, sorry, I was interrupted. All right, so the angular momentum is the same because the outside torque is 0. So there's no outside torque. So that's the first thing. Well, what happens to the angular speed? Well, since the angular momentum is conserved and the initial and final must equal one another, we know that the angular speed had to go down because the moment of inertia went up. So its angular speed has to go down. And the moment of inertia went up. Why did moment of inertia go up? Because I added mass to the spinning disk, because I was equal to the sum of all the masses times their location squared. And we now have a piece of clay on the edge of the disk. Okay. All right. I have a uniform board of length L, and I have a mass of M, a block of 4m on a fulcrum. So this is the board, which has a mass of mg. I have force normal up. I have mg pointing down here. I have 4 mg pointing down here. This length is L over 2. This length is L. They want to know A. Where is the location of the 4m block? The sum of the torques have to be equal 0. I know I have to sum the torques to find this answer because it has a distance. This we'll call torque 1. It's counterclockwise, therefore it's positive. This is torque 2. It's clockwise, so it's negative. Force normal and the force of gravity through the fulcrum do not cause a torque. Torque 1 minus torque 2. 0 equals mg. I have to multiply it times the distance away from its axis of rotation, minus 4 mg times some distance x. I will rearrange that for x. I will find x to be L over 8. I then have to find for B force normal, and I can sum all the forces in the y direction and set them equal to 0. Force normal is the only positive. Then I have minus mg, minus 4 mg, minus mg from the board, and I can find force normal to be equal to 6 mg. I have a wheel of mass m that rolls down a hill. I have force normal up. I have force of static friction up parallel to the surface. and opposite motion, and I have force of gravity downward. And so there's A, drawing a free body diagram and showing exactly where everything is acting. I should probably draw force of static friction a little better. B, which force causes, so there's A. B, only the force of static friction, because it is the only force that causes a torque on the wheel. Torque is the force times R times sine theta. It's the only one that has an actual R value if I have my axis of rotation right through the middle. Force normal has no R value, so neither does force of gravity. C, if static friction acts on the wheel at 50% of the force or force component that's directed opposite to the force of static friction, find the linear acceleration. I'm going to redraw that free body diagram. And now I have force normal up. I have force of gravity this way. Actually, let's just draw a dot. Let's make our lives easier. At this point, we can just draw a dot. Force normal, force of gravity, force of static friction. I'm going to break that force of gravity up into its components. That is not cosine theta. It's down an incline, so that is sine theta. There's theta, there's alpha, there's theta again. This is force of gravity cosine theta. Okay, I'm going to, for C, find the acceleration in the x direction. So I'm going to sum the forces in the x direction is equal to mass times acceleration, which is equal to Fg sine theta. That's my positive because it's to the right, minus force of static friction. They told me my force of static friction was 50% of the force that was opposing it, which is the force of gravity, the component of force of gravity. So that's 0.5 times Fg sine theta. We're going to subtract 1. This is an imaginary 1 right here, and this is a half. 1 minus a half is a half. So we get m times acceleration times 0.5. What is Fg? That is mg sine theta. Cancel the m's. Find acceleration to be equal to 0.5 g sine theta. Okay. Solid block and a sphere of identical mass are sent up a ramp at the same linear velocity, because they said speed. If they told me, if it was angular, they would have told me angular speed. Which one goes to the highest? Well, the answer is the sphere, because it has both a kinetic energy translational and kinetic energy rotational. So its total kinetic energy is higher, which will equal the potential energy of gravity at max height. So that's the reason. All right, this is actually, we haven't done this in class yet, but I'll go ahead and do it. This is actually the same as our lab. Some students want to determine the effect that different torques have on the change in angular momentum. So let's look at that equation. We know that if I put a torque on an object for some time, I'm going to change the angular momentum. Okay, and we also know that torque, the sum of all the torques, is equal to I alpha. Okay, so the solid disc has a radius of 30 centimeters and can spin without friction. The student performs an experiment where they apply different forces, one trial at a time, on the edge of a disc that's perpendicular to the radius. The forces are, so let's just imagine what that looks like. So here's my disc. I have some force, right? They're going to apply it for the same amount of time. The disk starts at rest, so we know the initial velocity is 0. And the students must measure the final speed after each force, or they do measure the final speed. So now I have my angular speed, the final, and we know our force. We can calculate our torque in Newton's meters, and that is torque is equal to R times the force, and it's perpendicular, so it's sine of 90, which is 1. So I'll do it for the first one. We know R is 30 centimeters, so R is equal to 0.3 meters. So I'll do for 1. And so the torque, the first one is 2 newtons times 0.3, which will give me 0.6. And so you fill that out for each one, okay? Before I figure out what else I need to figure out, let's see, what are they doing, essentially? Name the independent variable and the dependent variable. So what they're doing, all right, so they're finding the angular speed. So they want the independent variable and the dependent variable. The independent variable is what we're changing. So the independent variable is the torque that you're changing, which essentially is the mass. And the dependent variable is what we're measuring, which is the final angular velocity. Okay. What is constant? Well, we kept the time constant. The moment of inertia, or the disk rotational mass, was constant, and the radius of the disk was constant. All right. Determine what should be graphed so that the slope of the best fit line will give you the moment of inertia for the disk. There's more than one way to apply this. So I just know all these things. I know torque times some time is equal to the change in angular momentum. And we also know that the torque is equal to I times alpha times the change in time. Hold on 1 sec. Let me think. I know I could do this more than one way. Change in angular momentum is equal to the angular momentum final minus angular momentum initial. Angular momentum initial was 0. Angular momentum and final was I times my speed final, my velocity, what am I trying to say? My angular velocity final. And then on the left-hand side, I have torque times time. Okay. I want my two variables on the left side. So I have my torque and my final angular speed. So I have torque over angular speed equals I over delta t. Yep. I can graph this on my y-axis and this on my x-axis. Okay, that's one way. I could have also summed all the torques and said they're equal to I times alpha. We know the torque. We could find alpha. Alpha is acceleration. And I know the initial speed is 0. The final angular speed we found, so we're going to measure. And I have time. So I can find alpha. So another option is to put torque on the y-axis. So rearrange the torque over alpha equals I. And this is on the y-axis, and this is on the x-axis. And then the slope is directly y. And this is the slope is y over the change in time. Either way, okay? You will for sure get a straight line, and depending on which one you graph, you would have to calculate those things. Calculate either, heck, you don't have to calculate anything if you use angular speed. This you have to calculate angular acceleration. You'll get the same thing. Try it. All right, how would the graph look differently if there was a considerable amount of friction acting on the disc? Explain. How would it? So let's assume we do torque over acceleration equals I. So torque, acceleration. How would the graph look differently? Well, if there's a considerable amount of friction, the slope, which is equal to I, would not change. However, the amount of torque required to actually even create acceleration would be increased to something that overcame the friction. So it would move up the y-axis. Your intercept would be much higher. Okay, so that is my part 1 video for rotational equilibrium and dynamics. And I'll make another one for the second part of this worksheet.